Alright, hello class. In this lesson we're going to be talking about limits at infinity. So in the last lesson we talked about infinite limits. So that was where at some finite value the function blows up, right? That was a constant over zero case. For this we're looking at almost the opposite phenomenon. We're looking at what happens to a function as x increases without bound. All right, so when the x goes out to positive infinity or negative infinity, basically what is f doing? What is the function doing? Is it leveling off to something? Is it also blowing up? Those are essentially the two possibilities, or maybe it just doesn't exist, like if it's a trig function, okay, like an oscillating function. Okay, so let's give a couple of definitions here, and we'll start talking about how we analyze these things. In the past, you've probably studied this under what was called end behavior. Okay, basically what happens to the graph on the right and the left, what is happening at the end. So we don't really care about what's happening, say, around 0, but maybe out past like 10 million. All right, so the limit as x goes to either plus or minus infinity describes the behavior of f of x as x increases or decreases without bound. So we're talking about an increase if x is going to positive infinity, and a decrease if f is going to negative infinity. Hopefully that should be kind of self-explanatory. And there are three options. Basically, the limit as x goes to plus or minus infinity of f of x equals L if f levels off to L. Okay, so for example, if we're talking about something like this, where the function just levels off to L. Okay, so there the limit would exist and would be whatever L happens to be. Okay, of course the other possibility, and I think what most people would consider most common, but it's not, but it's probably where your head would go to first, is that if f increases or decreases without bound as x goes to plus or minus infinity, then like before, we say that the limit is infinity. So this would be things like, functions like this, that as x increases without bound, so does f, or as x decreases without bound, so does f. Okay, but it can also be situations like maybe the function increases without bound on both sides, or maybe it decreases on both sides. All right, there are a lot of possibilities here. Okay, and then the third possibility is basically the limit could just not exist. Right, there are quite a few ways we could make that happen, but we could have, say, a function that just oscillates like sine or cosine. Right, it never levels off, nor does it blow up. Or it could just blow up in two directions at once, which may sound like an odd thing to say, but for example, if this was our graph, say it did this, well, it's, half of it is going to positive infinity and the other half of it is going to negative infinity. So this would just be, it does not exist. Okay, so these are essentially your three possibilities that you can have for the function behavior, and it's probably not that brand new. I mean, this, like I said, was described in your pre-calc class as end behavior, or left and right behavior, and we're just formalizing it here. Okay, so as I said, this is just formalizing this concept from pre-cal that you've probably studied before. All right, so let's take a look at some examples here. All right, so let's look at a couple of just graphical examples here to kind of show what we're talking about here. And this hopefully should be more review. I think the important part of this lesson is really how we do this analytically without a graph. But when we have a graph, what we're really looking at is just what's happening from the left and the right. All right, so here's a quick little graph I threw together, just a typical polynomial function. And if I reduce this down a little bit, maybe it's a little easier to see what's going on here. Then as our x's are increasing, right, so look at how far I've zoomed this. My y-axis is going ticks of 20,000, and we can see that as x increases, so does y. Okay, so on this side, as x goes to infinity, f also goes to infinity. Okay, so here I've written it down. The limit as x goes to infinity of this red graph, I'm just calling it f, equals infinity, right? Now, similarly here, as x goes to negative infinity, so as x decreases without bound, well, so does f. F decreases down to negative infinity as well, right? So I can say that in this case, the limit as x goes to negative infinity of f of x is negative infinity. Okay, now something to mention here. If I go back to the default view, all right, and we see here that, okay, if I zoom out a little bit, this probably looks like a function you've seen before. It looks like maybe a degree 3 polynomial. Okay, so yeah, if I do this, this probably looks like something you've seen many times in your pre-calc classes. Okay, however, when we zoom way out, all of this detail disappears. Okay, especially if we go way out. Now this just looks like x cubed. Okay, in fact, this function is actually x cubed minus 6x squared minus x plus 3. Okay, when we zoom out far enough, we see that it loses all this information here. In fact, here in blue, this is just our normal x squared, or not x squared, I'm sorry, x cubed, right? And here, they don't look similar at all, right? We're back close to 0. But if I start zooming out, right, eventually what you start to see is the further I zoom out, the closer and closer these two graphs seem to be. Okay, so on a large enough timeline, right, if we zoom out far enough, now we've zoomed out a lot, right? Our y values here are, what is that? My R's aren't what they used to be, but this looks like maybe 10 million. And our x values, the tick marks, are 200. When we zoom far enough out, we can't actually see a difference between f of x and x cubed. All right, so this is just something interesting to note here, is that when we zoom out far enough, f of x looks no different than just x cubed. And x cubed is just the leading term of f. All right, if we look at another example, just to show that it doesn't always line up, like f doesn't always go to infinity as x does, or negative infinity as x does. If we zoom this particular function out, okay, we see that as x increases, this function is dropping down to negative infinity on both sides. So as x goes out, f is going down, and as x goes to the negative values towards negative infinity, f also drops down to negative infinity. Okay, so this particular function, I'm just calling g in this case. As x goes to infinity, g goes to negative infinity, and as x goes to negative infinity, g also goes to negative infinity. So what this is basically telling us is on the left and the right, this function drops down to negative infinity. Now, this particular function, okay, was actually negative 2x to the fourth plus 5x cubed plus 2x squared plus x. All right, so as x goes to infinity, right, we can speculate that x to whatever power is also going to be going to infinity. Right, so as x goes to infinity, x to the fourth goes to infinity, okay, x to the third goes to infinity, x squared goes to infinity, and x goes to infinity. Okay? I mean, that hopefully isn't too mind-blowing there, because as x increases without bound, like if you take something like 10 million, right, and then you raise it to the fourth, that is going to be a gigantic number, right? So this is 10 to the, what is that, 7? Okay, so that means x to the fourth will be 10 to the 7th to the fourth. All right, which is going to be 10 to the 28th power. That is 1 with 28 zeros. Right, so that's 1, 1, 0, 0, all the way, right, 28 zeros. I'm not going to write them all, but 28 zeros. Okay? All right, but, okay, so each one of these things is going to infinity. Now that, multiplying it by negative 2, that's going to then multiply this by negative 2. So negative 2 times x to the fourth would be negative 2 times 10 to the 28th. Okay, so as x goes to infinity, negative 2x to the fourth goes to negative infinity. Oh, okay. So when we put all these little pieces together here, right, as x goes to infinity, negative 2x to the fourth plus 5x cubed plus 2x squared plus x, that is going to go to negative infinity. This will go to plus infinity, plus infinity, plus infinity. Right? All these are going to infinity. Okay? But what you might think here, if you applied normal math, right? Applying normal math, you might think that negative infinity plus infinity would cancel out, and you get plus infinity, which would be, say, two infinities together should give us infinity. However, this is not the case, because if we go back to the graph, we see that, well, on this side we should get negative infinity. Okay, so what this tells us is that normal math does not imply or apply to infinities. Okay, because this, as we saw from the graph, goes to negative infinity. But how is it that all of these positive infinities can come together with this negative infinity and still be negative infinity. Well, it has everything to do with which piece is going to infinity faster. Because as we said, when x is 10 million, right, that's 10 to the 7th. As we said, 10 to the 4th is going to be 10 to the 28th. Or sorry, x to the 4th is going to be 10 to the 28th. That's 28 zeros, right? On the other hand, x cubed, I'll do that over here, x cubed will be 10 to the 7th to the 3rd, right, which will be 10 to the 21. Okay, so at this x value, we're going to have, when it's 5 times x cubed, it's going to be 5 times 10 to the 21. Right, when we square it, x squared will be 10 to the 7th squared, okay, which will be 10 to the 14. All right, and then just normal x is going to be our 10 to the 7th. Okay, so let me clean this up a little bit. All right, so for our g of x, which is negative 2x to the 4th plus 5x cubed plus 2x squared plus x, when we plug in x equals 10 to the 7th, okay, applying what we just talked about, we're going to get negative 2 times 10 to the 28th plus 5 times 10 to the 21 plus 2 times, maybe I shouldn't use x here, times, I'll use the dot, okay, times 10 to the 14th plus just 10 to the 7th. Okay, this guy has 28 zeros. This guy has 21. This guy has 14 zeros, and this guy has 7. So when it's all said and done, when we plug in 10 to the 7th, we get this number here. Okay, that's all said and done, we get this. Negative 2 times 10 to the 28 is this huge number here, which goes right off the screen. Okay, then we add this number, and we add this number. So these guys, right, will affect this, but like not by much. This is going to be like a negative 1999999, and then some other junk here. It's not really going to mess with this very much. Okay. This is still going to be an extremely large negative number no matter what's going on here. And that was just at 10 to the 7. If x is equal to 10 to the 10, then x to the 4th, like 2x to the 4th, let me say the whole thing here, negative 2x to the 4th is going to be negative 2 times 10 to the 10 raised to the 4. So that's going to be 10 to the 40. And then the next term over, this 5x cubed, right? That's going to be 5 times 10 to the 10 cubed. So that will be 10 to the 30. Well, this has 10 whole zeros over this one. Okay, so yes, this is a large number. However, it pales in comparison to this number. All right, so that's why when we look at the graph here, we lose all the information about what's going on near 0, because the stuff close to 0, okay, went in the wrong direction. Well, that's where around here, that's where the plus 5x cubed and the plus 2x squared, and those things are going to affect, what's going on. All right, and that's also why when I graph this alongside just negative 2x to the fourth and start zooming out, eventually these two graphs will start to look the same. Okay? And there we go. If I zoom out, whoops, that's probably way too far. But as you can see, this in blue is just negative x to the fourth, and we now can't tell the difference between the two. And that's why. It's because as we go further, this negative 2 times x to the fourth totally outclasses everything else, and eventually the graph just looks like negative 2x to the fourth. All right, so to recap this a little bit, for our function g, as x goes to infinity, the negative 2x to the fourth eventually completely outclasses all the other smaller terms. Okay, and so basically g of x eventually becomes negative 2x to the fourth as x goes to plus or minus infinity. So for this function, it was true on either side. We mainly more closely looked at the positive side, but everything I just said is also true for the negative side. So eventually it is the leading term that takes over completely. Okay, and since it is that leading term that takes over completely, for any polynomial, all right, we can basically reduce this down to what's happening with the leading term. And it doesn't even have to be polynomials. It could be really any power type function. Okay, so if f of x is a polynomial or a function including only powers of x, okay, so the main difference there is that a polynomial only includes a positive whole number powers of x. So that would be like 5x to the 10th minus 3x to the 4th plus, let's say 40x plus 10. Okay, but the other thing I just mentioned could involve things like x to the 2/3, okay, minus x to the 7/5. Okay, so that's the other piece. But really, we're mainly talking about polynomials here, but a lot of what we're talking about can also correspond with this, provided the function exists where we're talking about. You have to be careful with negatives with things like this, negative x's. But anyway, so if this is the case, then the limit as x goes to plus or minus infinity of f of x is going to essentially be the limit as x goes to plus or minus infinity of some power function. Okay? And where this cx to the n is the leading term of f of x. Okay? And then from here, we have some really quick ways that we can determine what's going on. Right? The limit as x goes to plus or minus infinity of x to the n is going to be plus infinity if n is even. Right? Because if n is even, whether we put pluses or minuses in here, we're always going to get positives, right? Even powers make anything we plug into it positive. So we'll always go to positive infinity. Okay. But if we have an odd power, so the limit as x goes to positive infinity of x to the n will be positive infinity, and the limit as x goes to negative infinity of x to the n will be negative infinity if n is odd, right? So odd exponents preserve negatives, while even exponents get rid of negatives. Okay? And then if we have a negative coefficient, it will reverse these, right? So, for example, I know that the limit as x goes to plus or minus infinity of, let's say, x to the fourth will be infinity, right? Because whether I put large positive or large negative numbers into here, we're going to get large positive numbers. However, if I throw in, let's say, a negative 5 in front of this x to the fourth, that's going to change that to negative infinity, because that is going to turn everything negative. Okay? However, if we have something like the limit as x goes to negative infinity of x cubed, well, negative infinity x cubed, I know some students will write this. They'll do negative infinity cubed, and then they'll put negative infinity. While you're still learning, there's really nothing wrong with this. Some people will sort of scoff at this, say you shouldn't do this, but honestly, when you're just learning this stuff, I see nothing wrong with that. So the limit as x goes to negative infinity of x cubed is negative infinity. However, if we change this to x going to negative infinity of, let's say, negative 5 times x cubed, okay, that's going to be a negative 5, okay, times negative infinity cubed. So it's a negative times a negative, right, which is going to give us a positive infinity. Okay, so the limit as x goes to negative infinity of negative x cubed, well, this goes to negative infinity. I'll sometimes just write this like this. So I have a negative times a negative, which will be a positive infinity. So a lot like last time, a lot of times what we're doing with these things is just trying to figure out whether what we're talking about is just positive or negative. Because once we get that, the fact that it's going to be infinity is a given. All right, so for another example, let's look at this particular graph. I switched over to a different software for a minute here. My other one was having trouble. But if you look at this particular graph, okay, we'll see that as x increases, okay, what happens as x increases without bound is that the graph itself levels out to negative 2, whereas as x goes to negative infinity, right, increases without bound in the negative direction, it goes to positive 6. Okay, so calling that function h of x, we could write this as the limit is the limit as x goes to infinity of h of x is negative 2, and the limit as x goes to negative infinity of h of x is 6. Okay, so as we talked about in the last lesson about vertical asymptotes, these limits at infinity give us horizontal asymptotes. So in this case, the definition is if the limit as x goes to infinity of f of x is L, then the line y equals L is a horizontal asymptote of f. And similarly, if the limit as x goes to negative infinity f of x equals capital M, then the line y equals m is a horizontal asymptote of f of x. Now, often m is equal to L. They're the same thing, but not always. Okay, so like in this case, y equals negative 2 and y equals 6 are horizontal asymptotes of h of x. Okay. Often they are the same, but they don't have to be. And be really careful, just like with vertical asymptotes, we're talking about the line. Okay, because if we were to graph these two lines, okay, so back to the graph here. I'm not as zoomed out as I was before, but here's the line y equals 6, and as you can see, the graph is starting to approach y equals 6, and here we have the graph y equals -2, and our original graph is approaching both of these lines as we go forward. Of course, a lot of times the asymptote is the same on both sides. All right, here's an example I appreciate a lot actually, because with this graph, if we just look at it in this particular window, it doesn't look like anything is happening as x goes to infinity. Right, you might say, well, there doesn't look like there are any limits at infinity. It doesn't look like there are any horizontal asymptotes. However, if we zoom out on the x-axis, okay, we can start to see that, yes, this function does oscillate, but eventually it is getting closer and closer and closer to the line y equals 2. Right, so if I graph y equals 2 real fast, okay, it's kind of hard to see. There we go. So we can see that here's y equals 2, and that is what our graph is getting closer and closer and closer to, okay, as we go out further. However, this function still oscillates. Okay, I've zoomed in closer so you can see, but this function is always oscillating. However, it gets closer and closer, okay, as x goes out further and further. Okay, so while at first it may have looked like, before we zoomed out, that we had no horizontal asymptotes, it turns out that the horizontal asymptote for this function is y equals 2, right? And that matches on both sides. All right, so here's another graph that on our default window here doesn't seem to be telling us much. I'm going to bring this up a little bit here. Okay, so the thing about infinite limits at infinity is this window that we're looking at may not be telling us anything. It looks like, well, it almost looks like a bird or a mustache. So let's zoom out or give ourselves more in the x direction. Okay, so it looks like this is going on here, and oh, maybe you can't see it, but maybe, perhaps we're leveling off at the end here. All right, maybe that's what's happening, but it turns out as we go further and further, it turns out that this graph is oscillating back and forth between -1 and 1. So this particular function never levels off, therefore its limit on either side does not exist. Right? Because the graph never levels off. It never gets closer and closer to, say, 0 or 1 or 10. It doesn't blow up either, right? So it doesn't level off, so it doesn't do that. It doesn't, say, blow up, right? It just oscillates back and forth. Now it does so quicker and quicker as time goes on, but it never actually levels off to anything, right? So this means we have a situation where the limit does not exist. Okay, now if we adjust this a little bit and look at sort of this other example, it looks like just what we're looking at here, this particular graph that I've just put. Oh, it looks like that as x goes to infinity and negative infinity, this graph is going down to negative infinity. However, when we move our x's in, we start to see more graph. And if we do the same thing in the y, oh, this is some strange behavior here. And in fact, if I zoom it out in both directions, we start to see that this graph is oscillating and increasing and decreasing without bound. Oh, okay. Well, this still does not exist because part of the graph is going to positive infinity, but the other part is going to negative infinity. Okay? Here I've sort of charted out where the max and min, or peaks and valleys of this graph are hitting, and as we can see that, yeah, this graph is sort of blowing up in both directions at the same time, so this is still a does not exist. Okay, however, on that smaller window we looked at, it was hard to see that. It actually looked like it might be going to positive and negative infinity. Okay, so like before, like always, we can't always count on a graph. So what do when we can't count on a graph? We have to come up with algebraic ways to analyze limits like this. And so that's what we're going to do for the rest of this lesson. Okay, so just to write that down, like before, we can't always rely on graphs, so we must find algebraic ways to analyze limits at infinity. Okay, so how do we do this? Well, we can break it down to a very particular case. So we talked about the 0 over 0 case. We've talked about the constant over 0 case is plus or minus infinity. Now we're going to talk about the constant over infinity case. Okay, so the constant over plus or minus infinity, it's really not, the plus or minus is not going to matter that much. It turns out that if we have a constant over infinity, okay, that's 0. Well, why would that be 0? Well, if we think about it, if we take, let's take something like 5 over x and think about as x goes to infinity and x goes to negative infinity. Okay, well, if x is, say, 10 to the 20th power, right? 5 over that's going to be, well, that's 5 over 1 with 20 zeros. All right, we're going to go all the way off the screen here. That is really small. In fact, if we do our sort of division power rule idea, this is 5 times 10 to the negative 20. Right, so that's 0.00000, all right, and we'll go out, I guess, 19 times and put a 5. Okay, so what we end up with is this really small number here. But the thing is, since x is going to infinity, we're going to get even smaller. We're going to go out even further. We're going to look at something like x equals 10 to the 100, right? So we'll have 99 of these zeros and then a 5. And the same thing is going to happen when x is something really large but negative. So when we have negative 10 to the negative 10 to the 20th. Now, keep in mind, I'm making this a negative 10 to the 20th, not negative 10 all to the 20th. Right? I want to keep this negative. Our 5 over x is going to be this same number here, just negative. Right? So it's going to be negative this guy. Well, that is still extremely close to 0. In fact, any sane person already would go ahead and round these guys to 0. So, it turns out, as I just said, that a constant over infinity case is 0, and that's plus or minus. Now, how do you remember this? Well, we already know that a constant over 0 always gives us a plus or minus infinity. We talked about that last time. Well, if you just divide by the infinity and multiply by the 0, right, move these around, sort of fake math, you get this one, which is the plus or minus infinity. When we divide c by it, it gives us 0. Okay? Now, the beauty of this is that this can work for all sorts of things, right? So the limit as x goes to infinity of, let's say, 1 over x to the 10th, well, we already know that x to the 10th as x goes to infinity is infinity. So this is a 1 over infinity case, which is just 0. Okay, so if we have the limit as x goes to negative infinity of, let's say, 10 over, let's say, x squared. Okay, actually, no, let's do x cubed. Okay, well, we know that as x goes to negative infinity, x cubed goes to negative infinity, which is going to be 0. All right, now, once again, I should say that there's some people that would scoff at us for writing this 1 over infinity step or this 10 over negative infinity step. However, when we're still learning, I see nothing wrong with this, right? I find it even easy to talk about or figure out which way this is going by writing it out like this. Okay, so really, nothing wrong with doing it this way. All right, so to do a couple more examples here, let's say we have the limit as x goes to infinity of, let's say, 10 over the square root of x. Well, again, if we think about this as 10 over the square root of infinity, well, what's the square root of infinity? Well, that's still going to be extremely large, because if you think about putting your x's in, let's say the x you choose is like 10 to the 100, then the square root of that is going to be 10 to the 100 square root, okay, which is essentially the 1/2 power, okay, which will be 10 to the 50. So this is still an extremely large number, right? This is 1 with 50 zeros. So it's still going to infinity, just maybe not as fast as x or x squared or anything like that, but square root of x still goes to infinity as x does. So this will still be 10 over infinity, which will be 0. However, something to be careful about, okay, would be something like this. The limit as x goes to negative infinity of 10 over the square root of x. This is going to be a does not exist, right? Because we can't have negative square roots if we're talking about real numbers. So that will be does not exist. Okay, so the question then is, well, how in the world are we going to use this idea that constant over infinity equals 0 to analyze anything? Well, to answer that, I think it'd be probably best to come back in a part 2 of this, since we've already taken a lot of time to develop everything up to this point. But from here, we're going to be able to get a lot. So we'll come back in part 2 and tackle this. All right, and I'll catch you all on that one. Cheers.